Now we will talk about dynamic logic circuits. When we look for a high density or a high performance digital implementation, what will be our major objective? We have to reduce the circuit delay and also at the same time we have to reduce the silicon area. So in this case, a dynamic logic gate offers them many advantages when compared to static logic circuits. The operation of all dynamic logic gates depends on a temporary storage of charge in this parasitic node capacitance instead of relying on a steady state circuit behavior. So in this case, we need to update periodically the internal node voltage since stored charge in a capacitor cannot be retained indefinitely. So, dynamic logic gates require periodic clock signals to control the charge reflection. We have already studied the static Cmos network in our previous classes, and you know that it can be realized by using both NMOS and PMOS network both connected as complementary. You know that NMOS network will be connecting as a pull down network and PMOS network will be connecting as a pull up network, and you will take your output from between the pull up and pull down network for a static Cmos circuits. So, but when we go for a dynamic logic, we need to use, for implementing dynamic logic, we need to use either pull up network alone or pull down network alone with the two additional transistors. So that's what dynamic logic we are implementing. So if you are dynamic logic, we are choosing only pull down network. So whatever the expression given to you, you have to implement by using pull down means NMOS network. So by using the NMOS transistors, and these are your primary inputs whatever you are giving over here, and implement the expression by using NMOS logic, and that is your that logic forms here. Then with the two additional transistors, so one is a header transistor which is a PMOS transistor, and another one is a phototransistor which is an NMOS transistor. So both will run by a common clock phi which is being applied, and as we will take your output from the drain of the means an upper part of pull down network. That means it will come as a drain of your NMOS transistors. So that is what a phi n network. The same expression you can implement in dynamic logic by using a phi p network, where we will use only pull up network. So whatever the given expression, that you will implement by using the PMOS transistors alone and only with the pull up part, and then these are your primary inputs. Accordingly you will apply, and then you will take your output. So for a PMOS network you will take the output from the drain part, that will be down. For a PMOS, drain is down and source is up. So your output you will be taken from here, and here also with the two additional transistors. One is the header transistor, that is a PMOS transistor, and another is a phototransistor, that is an NMOS transistor, both run by the same clock. So this is what is dynamic logic what we are implementing. So either you need a pull down network with two additional transistor, or you need a pull up networks of CMOS with two additional transistor. So in CMOS you use 2n transistor because you need both pull down and pull up network. So you need 2n transistors. If n inputs are there, you need 2n transistors. But here if you have n inputs, you need n plus 2 additional transistors only. So there is a significant reduction in the number of transistors when you go for dynamic logic. So now we will talk about the advantages of dynamic logic over static CMOS circuits. So as I told you, we need n plus 2 transistors instead of n input. For an n input function, you need only n plus 2 transistors for dynamic logic. But for a static logic, we need 2n transistors because we have both NMOS and PMOS network. So of course, compared to complementary static CMOS, better than n plus 2 is always better than 2n transistors. And also the performance is comparable to n plus 1 ratioed logic. So already we discussed about the ratioed logic. There they have only n plus 1 transistor, one extra transistor. So here n plus 2. So it is comparable only. And the performance wise also it will be comparable to ratioed logic. Now next is the load capacitance. The load capacitance is 50% less than that for a static CMOS and is also very closer to that of a pseudo NMOS circuit. So that because here if you are cascaded stages are there, so the output goes to the next stage. It's only having next stage is only also having only either an NMOS network or a PMOS network, right? So when the output goes to the next stage only to a NMOS or a PMOS network. But if in the case of static, it has to go to both NMOS and PMOS network. So because of that, our circuit operation is much faster than compared to a static CMOS gate. Around for dynamic logic, around 4 times faster than static CMOS circuit. So the next advantage is it is only having a very small static power dissipation. See, at any point you know that you have a PMOS and NMOS extra transistors as a footer and header network over here. So when we apply a clock at any point of time, only one transistor will be on, another will be off. So there will not be no direct path from VDD to ground. So absolutely speaking, there is no static or a very smaller amount of static power dissipation in dynamic logic circuits. Now next is there is no short circuit power dissipation when compared to static CMOS circuits, because when in the static CMOS circuit, when input is changing from 0 to VDD, the region between VTN and if you just recall the working, the region between VTN and VDD minus VTP, there is a short circuit path through PMOS and NMOS network. So here it won't occur because the operations are in two phases, either pre-charge and evaluation phase, which is being already explained to you. So in the previous video. So since the operations of the dynamic logic are in two phases, pre-charge and evaluation phase, there will not be no short circuit power dissipation happens in dynamic logic. Last advantage is there is no glitching power dissipation. Actually, in case of in case of static CMOS circuits, depending on the change of input, that is, if we keep on changing the inputs or in a multi-level network, the input can arrive at a different point of time. In that case, that may lead to change in the output from 0 to 1 or 1 to 0 before settling down to the final value. That means your outputs will be keep on changing before settling down to the final value. That's what the glitches happens. So this glitching effects is not there in dynamic CMOS, dynamic gates. Why? Because its operation is again in two phases, because pre-charge and evaluation phase. So because of that, we don't have a glitching power dissipation in dynamic logic gates. So these are the main advantages of dynamic logic gates. So considering all these advantages of dynamic CMOS circuits, it has got some serious disadvantages also. So the disadvantages of dynamic logic gates are charge leakage problem, charge sharing problem, and clock skew problem. So now we will discuss each of these in detail. So we will discuss the first one, first disadvantage of dynamic logic gates. It is a charge leakage problem. So already we know that we are realizing the dynamic logic gate by using an NMOS net. If you are using an N5N network, so we are realizing the dynamic logic gate by using a pull down network, that is your NMOS transistors. So this will be your NMOS network. and then you will be having two extra transistors, one NMOS and one PMOS. These are the two additional transistors, phototransistor and header transistors, and you are applying your input here. So this is your dynamic CMOS logic realization. And you know that this capacitor CL, it's not a discrete capacitor. It is an induced capacitance that is connecting to the next stage. So this will be acting as a storage element when you connect to the next stage. Okay, so what will happen during the pre-charge phase? What is pre-charge phase? When your phi is equal to 0. So this is what is your pre-charge phase, correct? So what will happen at the pre-charge phase? Pre-charge phase phi is equal to 0. This transistor will be off and this transistor will be on. So your output will be pre-charged to VDD. So your output will be pre-charged because this transistor is on. It will pre-charge to VDD. This is what is happening in the pre-charge phase. Suppose now evaluation phase starts. So in the evaluation phase, what will happen? Phi will become 1. So naturally this transistor will be off. So in the evaluation phase your phi will be equal to 1. So this transistor will be off, this will be on. And suppose that your inputs are in such a way that the NMOS network is off. So NMOS network is off means you are supposed to retain your output VDD because this is off means there is no way to discharge it to ground. So your output should be retained to VDD. But the problem is how long it will retain. So that suppose your clock is so long, your evaluation phase clock is bit pre-charge and evaluation clock is bit long clock. So how much time this output can be retained to VDD? That is the main problem, or there the first disadvantage of dynamic CMOS gate comes, the charge leakage problem. So the clock period is too long, then your capacitor C will start discharging, but your NMOS network is off, correct? So when the NMOS network is off, even though it is off, unfortunately there will be parasitic diodes through which your capacitance CL will discharge. There will be not one parasitic capacitance. There will be a number of parasitic capacitance that will form between the source and the substrate through which your capacitor CL will start discharge. So these parasitic capacitance will be reverse biased. So through this reverse biased capacitance, there will be a small reverse bias current through which the capacitor will be discharging. So, and we know that reverse bias current is normally small, but for a long duration, this current may not be small. So that means this capacitor will discharge, so the output voltage level will be degrading. So then for the next, when you connect cascade another stage to this, for the next stage, even though this output was high, but it will be interpreting as a low level. So the charge leakage problem we can explain by diode equation ID. ID is equal to Is into e raised to QV by KT minus 1, where Q is the electronic charge, V is the applied voltage, K is the Boltzmann's constant, and T is the absolute temperature. And we normally this current will be around 0.1 nanoampere to 0.5 nanoampere per device in room temperature. But this equation depends on temperature. So the temperature rises, this current will also increase. So the current will double every 10 degrees Celsius rise in temperature. So if the device is hot, the leakage current also will be high. So now so we can compensate this by refreshing the charge at regular interval. Another problem for this is a subthreshold leakage current. Subthreshold leakage current is a current that flows through the channel. So it is quite means it will be quite large when we consider in current technology, these deep submicron technologies and all. Subthreshold current will be quite high. So we can reduce the subthreshold current by increasing the threshold voltage. That is a solution for reducing the subthreshold current. So overall charge leakage problem you can overcome by using a high threshold voltage VT and also use a weak PMOS transistor as a pull-up device. So we will study about the circuit in detail when we study next disadvantage. So these are the two solutions for overcoming the charge leakage problem.